Kirchhoff's laws. Kirchhoff has given two famous laws, Kirchhoff's first law and Kirchhoff's second law. We will take one by one. Kirchhoff's first law is also called as Kirchhoff's current law. So we will take first Kirchhoff's first law. It is also called as Kirchhoff's first law. It is also called as Kirchhoff's current law or junction law. Junction law. It is very easier law to understand. According to this law, Kirchhoff's first law or Kirchhoff's current law or junction law, it states that the algebraic sum of current at any junction, in a given electric network is equal to 0. I know from statement you didn't get a better idea about this law. What is law? I have told you that the algebraic sum of currents at any junction, the algebraic sum of current at any junction, but where? In an electric circuit, in an given electric circuit, or you can say that electric network. What I have told you, the algebraic sum of currents at any junction in an electric network is equal to 0. Okay, this is the statement of Kirchhoff's first law. According to this law, we also write this Kirchhoff's first law, current law mathematically. That is, summation of I is equals to 0. What does it means? Summation of I means if suppose there are 5 different currents are flowing from a junction. Suppose I1 to I5. Then summation of I1 plus I2 plus I3 plus I4 plus I5 is equals to 0. I will, before taking one example to understand this law, I will give you some sign convention. With the help of that sign convention, you can apply this Kirchhoff's current law or junction law to any electrical network or circuits. So, what are that sign convention for this Kirchhoff's first law or current law? According to this, the sign convention of Kirchhoff's first law, if the current first rule is if current moving towards junction, if current moving towards junction treated as positive, otherwise treat it as negative. If a current moving towards a junction treated as positive. If suppose that current is not moving towards junctions, means suppose the current is moving away from junction, then in that case treat that current as negative. I will explain this law to all of you with one simple example. How you can apply the Kirchhoff's current law or junction law to any electrical network. We will just see this law with the help of example. As I know the statement, all of you got this statement, that is algebraic sum of current at any junction in an electric network is 0. So just we will make very clear this law with the help of one example. Suppose we have a junction. Suppose we have this junction. This junction has from this junction there are 5 different currents are flowing from this junction. Suppose I1 is the current which is equals to 2 ampere. I1 is equals to 2 ampere is flowing towards the junction. Second, I2 is equals to 3 ampere is current flowing. Instead of 3 ampere I will take it as a 4 ampere. I2 is equals to 4 ampere current is flowing towards junction. Then after that I3 is equals to 2 ampere current flowing away from the junction. Another I4 is equals to 1 ampere current is flowing away from junction. And last, that is I5 is equals to 3 ampere is current flowing from the junction. So if you apply Kirchhoff's current law to this junction, then we should satisfy this equation, that is summation of R is equals to 0. Means if you apply this law, according to law, the current flowing towards the junction will be treated as positive and the current moving away from junction will be treated as negative. So if we apply, then I1 is equals to positive. Why? Because I1 is the current which is flowing towards the junction. After that, we have second current I2. I2 is also a positive. Why it is positive? Because it is also moving towards the junction. Then we will take I3. I3 is a current which is moving away from junction. Therefore, we treat I3 as a minus. Or we can simply write their values. I1 is equals to 2 ampere. I2 is equals to 4 ampere. I3 is equals to 2 ampere. But we will take it as a minus. Why minus? Because it is moving away from junction. Then I4. I4 is also moving away from junction. Therefore, we will take I4 as a minus 1. After that, we have last, that is I5. I5 is moving away from the junction. So that is why it is also taken as minus. So if you add all this, 2 plus 4 is 6, then minus 2, minus 1 and minus 3. So it will become 6 minus 6. So answer will be 0. Therefore, summation of I is equals to 0. Means we have just added I1 plus I2 plus I3 plus I4 plus I5. And we will got answer 0. Means summation of I is equals to 0 for this circuit or for this junction. From this discussion, we can say that I1 plus I2 is equals to I3 plus I4 plus I5. We also can say that from this law, the summation of incoming current towards any junction, the summation of incoming current towards any junction is equals to summation of outgoing currents which is moving away from junction. Means for any junction, incoming current is equals to outgoing current. This is very simple. We can simply state like this also. For any junction, the summation of incoming current is equals to summation of outgoing current. This is all about the Kirchhoff's first law, or we can say that current law or junction law. I think from such a very little bit and short discussion, you have got the idea about KCL, that is Kirchhoff's current law or junction law. After that, we will move over towards next law, which is called as Kirchhoff's second law, and just after that, I will explain this article to you. Kirchhoff's second law. Kirchhoff's second law is also called as Kirchhoff's second law is also called as Kirchhoff's voltage law. It is also called as Kirchhoff's voltage law. Voltage law. In short, I will write it as a KVL. KVL means Kirchhoff's voltage law. First of all, I will write the statement of this law. Statement is very simple. if you know the mathematical statement, from that mathematical statement is you can easily write the descriptive statement for this law. The mathematical statement for Kirchhoff's voltage law is summation of IR plus summation of E. Summation of E is equals to 0. This is the Kirchhoff's voltage law. You can say it is the very single line, very 2 or 3 word statement in concept of math. But if you elaborate this concept of this statement verbally, then we can say that according to Kirchhoff's voltage law, summation means you have to add all the IR drops in a given electric circuit. IR drops means potential drops. It is the product of electric current and resistance. Plus you have to add all the EMFs in a given circuit. Means what you have to write in this law, the algebraic sum, or you can write for any closed loop, of what? For any closed loop of electric network, or you can say that electric circuit. For any closed loop of electric network, the algebraic sum of all potential drops, or you can say differences also, for any closed loop of electric network, the algebraic sum of all potential drops in that circuit plus the algebraic sum of all EMFs in given electric network is equal to 0. This is very simple statement of Kirchhoff's voltage law. I just write this statement from this very short mathematical statement. That is summation of IR plus summation of E is equals to 0, where E means EMF. How you can write this statement? Look, just here once again, for any closed loop of electric network. Closed loop of electric network means you have to take any electric circuit. For that electric circuit, the algebraic sum of all potential drops means you have to take the summation of all potential drops in that given electric loop. You have to add, and you have to plus these potential drops with the algebraic sum of all EMFs in that electric network is equal to 0. Means if you add all IR drops in a given electric circuit with the algebraic sum of all EMFs, then you will got the equation equal to 0. This is Kirchhoff's voltage law. I know this is very difficult to grasp the student from this statement. If I will take one example or one numerical example on this Kirchhoff's voltage law, you all have become very clear related to this article. There is no fear or there is no worry regarding to this article, because although statement is very looking dangerous, but it is not so dangerous. It is very simple topic if you know the further example on Kirchhoff's voltage law. Okay, so for making very much clear, this Kirchhoff's voltage law also has very important aspect, that is sign convention. If you know sign convention while applying Kirchhoff's voltage law to the any given electric circuit, then you did not make any single mistake to calculate the values of voltages and current in a given complicated circuit. It is very important for calculating the values of electric current, potential drops in given complicated circuit. You must know the sign convention while applying the Kirchhoff's voltage law, and that sign convention I will just write on a board. I think you have got the idea about this statement. If you have any doubt, then you can just ask me anytime. I will give my contact after my lecture if you have any doubt. Lastly, once again I will repeat this law, and after that I will take sign convention. Summation of IR plus summation of E is equals to 0 for any electrical network. This is very simple statement of Kirchhoff's voltage law or second law. To apply this law, we have to follow two sign conventions, or we can say laws or rules. What are those sign conventions? So first sign convention is, suppose we are tracing the loop, a closed loop, and suppose we are moving in a loop clockwise direction, and if you observe the current are also flowing in the clockwise direction, then in that case, if the direction of tracing of loop and the direction of conventional current flow is same for given electric network, then those current you have to take as a negative current. I will once again repeat. While tracing the loop for calculation of voltages and current, if you move the loop in an anti-clockwise sense, and if you observe some current also are flowing in the same direction of tracing the loop, then those current you have to take as a negative current, or otherwise you have to take it as a positive. If suppose you are moving in an electrical network as in an anti-clockwise sense, and some currents you are viewing that some current are moving in an anti-clockwise direction, in a clockwise direction, so that current you have to take as a positive. Means if the direction of tracing of loop and direction of current flow is the same, then those current as it will be taken as a negative, or otherwise you have to take it as a positive. This is the first important. The direction of tracing the loop and the direction of current is same, then in that case you have to take that current as a minus or negative. Second rule is, if you are tracing the loop, while tracing the loop, while tracing the loop, you will come across some EMFs or batteries or cell in a given circuit. While tracing the loop, if you come across some batteries or cell, and while tracing the loop, if you move from negative terminal of a cell to the positive terminal, then in that case the EMF of such cell will be treated as positive, or otherwise it will be treated as negative. Suppose while tracing the loop, if you move from positive terminal of battery to negative terminal of battery, in that case you have to take the EMF of that cell as a negative. So this is very important law. I know only orally this is very difficult to understand this sign convention. I will also write this sign convention on board. While writing, I will once again explain to you that sign convention. After that sign convention, we will take one more example to understand this Kirchhoff's voltage law. Why? Because if you know this Kirchhoff's voltage law, you will become very much clear to apply this voltage law for any electrical network. With the help of that electric network, you can easily understand any numerical in case of NEET or CET. So just going to the sign convention, if you have any doubt, then please comment. Sign convention for KVA. So first sign convention is, if the direction of conventional current flowing through circuit if the direction of conventional current flowing through circuit is same as that of the direction of tracing the loop, then that current taken as negative. Or otherwise it will be taken as negative. Taken as or treated as positive. This is the very important law and first law. According to this law, if the direction of conventional current flowing through the circuit is same as that of the direction of pressing the loop. Suppose we are pressing the loop in anti-clockwise direction, and in that circuit current is also flowing in the same direction, then that current you have to take as negative. If it is flowing in opposite direction, then you have to take that current as a positive. This is very simple and first sign convention. Second sign convention is that while tracing the loop, if we move from positive terminal of a cell, or you can say better. You can take this as same or better. Then, while tracing the loop, if we move from positive terminal of a cell or battery, then if we move from positive terminal of a battery, positive terminal of a cell or battery towards negative terminal, then such cells will be treated as negative or minus. Negative EMFs. Otherwise it will be treated as positive. This is very important law. While tracing the loop, if we move from positive terminal of a cell towards negative terminal, then such cells or EMFs will be treated as negative EMFs. Otherwise, if it will not happen such, like if you are not moving from positive terminal to negative terminal, suppose if you are moving negative to positive, then in that case you have to take that EMF as a positive EMF. So these are two important sign convention while applying Kirchhoff's voltage law. This voltage law will become very much clear to all of you if you refer my next explanation on applying this Kirchhoff's voltage law on a given circuit. First of all, I will draw a circuit. For that circuit, you have to apply this Kirchhoff's voltage law with this sign convention. Then, while applying this sign convention, you become very much clear about KVL, and after that, we will take some more example to calculate the values of different voltages and current in a given electric circuit. So, we will go to the example to apply this Kirchhoff's voltage law to a given electric circuit. First of all, I will draw an electric circuit. It consists of a EMF E1, a resistor. This is the resistor R1. It also consists another EMF E2, a resistor, another resistor, so another R3 is a resistor. This is resistor R1, this is resistor R2, R3, R4 and R5. And this is positive terminal of a cell, negative, positive and negative. We have this circuit as shown in board. It consists of two EMFs E1 and E2 with the polarities as shown in figure. It also consists of different resistors, that is R1, R2, R3, R4 and R5. Suppose a current I1 is flowing from positive terminal of a cell. It moves downward through resistors R2, this is I1. Another current I2 is flowing from cell E2. It moves towards a point. We first of all nomenclate this circuit with different points. Suppose this is a junction point A. This is another junction point B. It is point C. Another point here is it is D, E, F and A. Suppose this given circuit has different junction point A, B, C, D, F, E, F and A. So at point B you observe that the current flowing from A to B, that is I1, and the current flowing from C to B, that is equals to I2, gets added up here. And here the current flowing from B to E is nothing but the summation of two different currents, that is I1 plus I2. So this is the diagram. For this diagram we have to apply Kirchhoff's voltage law. So for applying the Kirchhoff's voltage law we have different closed loop. I have already more times used closed loop network. Then what is it? This is the closed loop network. It has different loop. First loop is A, B, C, D, E, F and A. This is the first closed loop. Second closed loop is A, B, E, F, A. Third one is B, C, D, E, B. These are different closed loop. And to this different three closed loop we have to apply KVL. Then why we are applying? So to calculate the values of I1, I2, R1, voltage across R2 means V2, V1, V3, V4 and V5. To calculate such potential drops and to calculate the different values of current, that is I1 and I2, we use Kirchhoff's voltage law. Then first of all we apply the Kirchhoff's voltage law to the loop. We take first loop as A, C, D, F, A. We have firstly we take a loop A, then C, after that D, after that F and A. Apply Kirchhoff's voltage law to this loop. You know we are moving A to C, C to D, D to F and F to A. Means our sense of tracing is in which direction? Anti-clockwise direction. And you see, as I move from A to C, I face two currents, I1 and I2. It makes two potential drops here. First potential drop is I1 R2 and second potential drop is I2 R4. Then whether these potential drops are positive or negative, we will apply sign convention to decide that. So while moving from A to B, we see that we are moving downward and the current is also moving downward. Means the direction of tracing the loop and direction of the current is same. Therefore I1 will be treated as yes, minus or plus, we have to take it as a minus. Why minus? Because it is moving in the same direction as the direction of tracing the loop. So therefore, the first IR drop, that is I1 into R2, will be treated as minus because the current is moving in the same direction. Then while moving from B to C, we observe that the current I2 is moving in the opposite direction of tracing the loop. We are moving B to C and then current is moving C to D. Then the direction of I2 is opposite to that of the direction of tracing the loop. Therefore I2 will be treated as positive and therefore we will take that potential drop, that is I2 into I4 will be positive. Okay. After that, as we move C to D, we have two components. First is EMF and second is R5. So, as we move C to D, we are moving from positive to negative. As we are moving from C to D, then in this case we are moving from positive to negative terminal of battery. And according to rule, if we are moving positive to negative terminal of a battery, then of a battery or cell, then the EMF of such cell will be treated as negative. Why negative? Because while going from positive to negative, the potential drop, the potential loses or potential become less. So while moving from positive to negative, for that case we have to take the EMF E2 as a negative, according to rule number 2 of sign convention. Now we will move towards next resistor R5. You know, here the current is I1 plus I2, but in this, at this point the current gets split up. The current flowing E2F is I1 and the current flowing through E2D is I2, and the same current is flowing through this resistor also, that is I2. And you know, we are moving C to D and current is moving D to C, means the direction of I2 is opposite to that of our direction of pressing the loop. Therefore I2 is it will be taken as positive, and I2 R5, this potential drop, that is this potential drop I2 R5 will be taken as positive. Why positive? Because the direction of current is opposite to that of the direction of pressing the loop. Now, as we move D to E and E to F, there is no component in this path. So therefore, there is no need to apply KVL for this path. As we move from F to A, we have two components, R1 and E1. So you know, the current flowing through this R1 is I1, and the direction of loop is F to A, and the current is also flowing in the same direction. Therefore, the potential drop I1 R1 will be treated as negative. Why negative? Because current has the same direction of loop. So now we will come toward this point, that is for say E1. While pressing the loop, we move from negative terminal of battery to positive terminal of battery, and according to sign convention, that EMF will be treated as positive. So it is equals to 0. Then this is we have applied Kirchhoff's voltage law to the loop A, C, D, F, A. While moving from A to B, I1, R2 is taken as negative because current has same direction. I2, R4 is taken as positive because current has opposite direction to the loop. Then we have taken E2 as a minus because we are moving positive terminal of battery to the negative terminal. The potential of I2 R5 is treated as positive because we are moving C to D and current is moving opposite to the direction of loop. Therefore, I2 R5 it will be taken as positive. Then there is no any component in this path, and as we move from F to A, we have observed that the current is moving in the same direction of the loop. Therefore, this potential drop will be treated as minus or negative, and EMF of cell, while pressing the loop, we are moving negative to positive terminal of a cell. Therefore, E1 will be treated as positive. So, just we have applied the Kirchhoff's voltage law to the loop A, C, D, F. Just we rearrange these terms. We know here I1, here term I2 and I2. We just rearrange this term and we will get minus I1 R1 minus I2 R2. These two terms we have written here. Then after that plus I2 R4 plus I2 R5 here, I2 R4, I2 R5, and after that minus of E2, and plus E4 is equals to 0. You take here, if you here I1, because I1 R1 minus and minus I1 R2. If you take minus I1 common, you will remain in bracket R1 plus R2. For this equation, if you take I2 common in bracket R4 plus R5, and here if you write it like this, E1 minus E2 is equals to 0, or simply you can write it as if you put this E1 and E2 on other side, then it will also okay. So we can write here minus I1 in bracket R1 plus R2 plus I2 R4 plus R5 in bracket, and here we can write it as a E2 will become plus on other side and E1 become minus. So just this two statement gives you Kirchhoff's voltage law that we have applied for loop A, C, D, F, A. Similarly, you can apply Kirchhoff's voltage law for the loop B, C, D, E, B, and for the loop A, B, E, F, A. Okay, so I think you have got the very brief idea about Kirchhoff's voltage law. After that, I have three loops here. I have applied Kirchhoff's voltage law to the bigger loop, and now I will apply the Kirchhoff's voltage law for the any one loop, if either for this loop or this loop, second loop. So I will apply Kirchhoff's voltage law for loop A, B, E, F, A, and you try at home to apply Kirchhoff's voltage law to B, C, to the loop B, C, D, E, B, and if you have any difficulty, then you can ask me at any time. Just you try at home to apply the Kirchhoff's voltage law to the second loop. Just I will once again explain this Kirchhoff's voltage law to the first loop. Okay, so we will apply it for another loop, and is equals to loop A, B, so that B to E, E to F, and E to F, A. Means we have taken this loop, E to B, B to E, E to F, and F to A. We have to apply Kirchhoff's voltage law to this loop. Then how you can apply in the same manner as you are moving A to B, current is also moving in the same direction. Therefore, this current will be taken as minus, and therefore this potential drop will be written as minus I1. Now we are moving from B to E, and I1 plus I2 is I1 plus I2. It is the current flowing through this resistor R3. So the direction of tracing the loop and the direction of current flow is same. Therefore, this potential drop I1 plus I2 into R3 is also taken as minus. Why minus? Because the direction of tracing the loop and the direction of current is same. After that, it is very much important while going from E to F, we see that there is no component. Okay. After that, while moving from F to A, we have two different components, that is R1 and E1. So we will apply Kirchhoff's voltage law to them. It is taken as minus I1 R1. Why minus I1 R1? Because current is flowing in the same direction as that of the loop. Therefore, it is taken as this potential drop will be taken as minus. And while moving F to A, we are moving negative terminal of battery to the positive terminal of battery. Therefore, E1 will be treated as yes plus. So it is equals to 0. It is equals to 0. This is the equation for Kirchhoff's voltage law. I can write it as I1 R2 minus in bracket I1 plus R2 into R3 minus I1 R1 plus E1 is equals to 0. Or you can also simplify this equation by multiplying R3 into the bracket, and you can write it as a minus I1 R2 minus I1 R3 minus I2 R3, then minus I1 R1 plus E1 is equals to 0. You know here I1, here also I1, and here also I1. If you take minus I1 common, you will get equation R1 plus R2 plus R3 for this first, second, and third. And what will remain? Here remain will be minus I2 R3 plus E1 is equals to 0. If you take I1, I2 on other side, you will got the equation here. E1 is equals to I1 in bracket R1 plus R2 plus R3, and this will become plus on another side. So I2, and so this is the important equation. This equation or the second equation. It will obtain to us after applying Kirchhoff's voltage law to the loop A, B, E, F, A. So like this you can apply Kirchhoff's voltage law to any circuit. I hope that you have got the idea. I know this is very bulky while writing the equation on board, drawing the diagram. It takes so much time and you can not tolerate such very heavy time while drawing the diagram. But for explaining some article, you have to just follow this step. Then only a very last student can also get the idea about the electric circuit. So I have applied KVL to out of 3 loops, for 2 loops I have applied and 1 loop I have remained for you. Just try at home, and if you have any difficulty then please you can ask me at any time. Okay, so with this very short introduction of electric current and Ohm's law and brief discussion with Kirchhoff's voltage law, first law and second law, that is KCL and KVL, we will stop here. And in our tomorrow's lecture, I will take some more example, numerical example, to apply Kirchhoff's voltage law to given electric network to find out the different values of current. I hope that you have enjoyed this article in very good manner. If you still have any difficulty, then you can just give or ask question at any time. Today we will stop here. Thank you so much.